Okay, let's start our second presentation. This will be about parsing code with the speed of light, and our today's speaker is Michael Matloka. So please give him a round of applause, and let's start.
To ja dzisiaj w międzynarodowym języku technologii, czyli in English. Hey all, awesome to see you all. So I'm Michael, and today I'll be talking about speeding things up, pedal to the metal. And now, don't get me wrong. You know how in Poland we have this saying, jeżdżę szybko, ale bezpiecznie? That's not what we'll be doing today. Jeżdżę szybko, ale bezpiecznie tends to end like this. So that's not how we'll be speeding up today, but we will be speeding up our Python backend by quite a bit. Today we'll be parsing fast and safely. So here's a sneak peek. Today we'll be parsing SQL select statements. That's basically the problem we've got. And we're looking at data from a real world backend here. And the yellow and green lines are the slow way. The red and blue lines are our destination. And we'll get back to this graph in a sec. Now let's kick things off. This is parsing at the speed of light. And I'll be trying to convince you that combining three things called Python, C++, and this mystery ingredient called ANTLR is a great thing. And it, in my work, has sped things up immensely. So, just one bit of background is why do we care about this SQL, about parsing SQL? So a very, very quick plug is that I work at this company called PostHog, and we help and we build tools for developers to build better products. And we also like hedgehogs. So actually there is a hedgehog in every single slide in this presentation. Look out for them. So, but for today's topic, what all that matters is that we allow you to write arbitrary SQL queries on your data in our platform. So you can write anything you want. And we've got a custom flavor of SQL called HogQL, pretty much like a superset of something like standard Postgres SQL. And there are two reasons we've done this. Two reasons why it's custom. So one is things can be a little bit more intuitive if you parse SQL yourself and then output that as your target, SQL for your target database where you're actually running the queries. And the other actually more important reason is you really want to prevent those SQL injection like Bobby drop tables right over there. And so the way you do it is you take this string of SQL, like the select foo statement on the left, you parse it, and that's what you get out of it is this, in this case, a select query object in Python. And then you're 100% sure this is all correct. And there's no funny business going on here. And finally, you print it out back to SQL. And maybe you add some other condition, like you're doing a multi-tenant service. So you actually want to only filter by that specific customer. So that's why parsing is great. So now the question is, how do we write a parser for something as complex as SQL? And you've got tons of features, like all the ways of writing a select query with group bys, order bys, different types of columns. So there is a lot of it. You can hand roll a whole parser on your own, but it's quite a bit of work. it'd be a lot of work here. So there's a slightly nicer way. And here, enter ANTLR. ANTLR stands for another tool for language recognition. And it's a parser generator. So what you do is you give it a beautiful definition of your grammar, like this. That's a snippet of our full SQL syntax right here. It's like 8 times this length, basically. So there is a lot of moving parts. But the nice thing about this ANTLR parser generator tool is it handles all this. There is no syntax it won't handle. And it can target a bunch of languages, including Python. So that's really convenient. And when you run the ANTLR command on this set of, on this definition of your syntax, you get a bunch of Python. And you don't have to do a lot to do that. So that is how ANTLR is able to represent a statement, a column expression actually, that looks like column expr is null or is not null. So it's a single rule for that specific case. And this is totally language agnostic. So actually this is not, this part works equally in TypeScript, Go, C++, Python, and a bunch of other targets that ANTLR has. So while that's pretty handy, you've just got to go through one more step. You've got to visit every rule, like that column expr is null one, and you just convert it to whatever abstract syntax node that is relevant for you in your backend. So an abstract syntax tree is just a tree that's the representation of, in this case, the whole select statement. And it's got a bunch of sub-nodes for operations, like we've got a compare operation here. So we don't care how it was written exactly. Maybe it was written as some different type of syntax, actually. But it's an AST compare operation, so that's what we'll need to actually do later on. So now that we've done this, we've taken the raw parsed nodes out of ANTLR, converted that to our tree. We've basically got everything to now print that back out into SQL, which is like, it's the inverse of this. It's actually way simpler. You just concatenate strings if you've got a compare operation with an operation that's equals. You can just print out the left side, add a string that's the equal sign, print out the right side, that's it. So I'm kind of going to omit that, since that's really simple and really fast. There is no bottleneck there. But there is a bottleneck here overall. So we've got a bunch of Python. You can see this is 6,000 lines of Python right here. Which actually you can't because of contrast. But that's 6,000 lines right there. So quite a lot of that. And that's not the end. That's just a small chunk of the whole auto-generated parser. So when you try to run this, it might take a while, like 120 milliseconds on average for a pretty basic select statement. And I checked these stats. The average select statement in our backend takes just 200 milliseconds to run in the database itself. So you're spending more than 1/3 the time just parsing the SQL in our backend before it gets to any sort of database, before we even print it out back into SQL. And the slowest 5%, that's around a second, a full second, just to parse an SQL query, which is not great for the product experience. I mean, if Postgres took a second to parse your query before it does anything with it, even an explain query, you'd probably ditch it pretty fast. So that's a problem. So the Python parser is a bottleneck. And then again, our whole backend is in Python. So we've got this bit of a problem. We don't really want to rewrite everything into Rust, even though that's pretty trendy. It might take a few $1 million. Well, and that's underestimating it. So, man, if only we had a language that's way faster than Python, that is a supported ANTLR target and can interface with Python easily. And it's not Rust, because Rust has a very alpha target for in ANTLR, but you really don't want to use it. And well, from what I've tried, it literally does not work. So we've got to find a different way. And a pretty cool one is, when you think about it, maybe it's Python. So Python is written in C. Well, C Python is written in C, but almost everyone uses C Python, which we are looking at right here. That's C Python code from master right now. And you can see it's got this underscore prefix function, which you cannot use. Don't ever think about it. And then you've got this pylist append, which you can very much use. And you can just call it yourself. So if we just use ANTLR as the target for our parser and try to combine that with all that's going on here, literally plug into Python at a pretty low level, we're still going to be able to use Python, and it's going to be a little bit faster. So let's try this. And it looks pretty much the same. So it's pretty much the same structure, just the language has changed. We've still got the same column expr is null rule. And we've got to do the same thing. We've got to write some code ourselves. That's our code right here. Like, it's a pretty big parser.cpp file, but it does the same thing we did in Python. It for say the column expr is null rule, we create this compare operation object in Python, and that's the key thing. That we are not returning something that's totally that we have to serialize somehow. We just create an object in Python's memory directly, just with this. So that's a lot of code here. So just in case you were wondering how to actually instantiate a module like this, and I was, so I had to read a lot of documentation to do just this, because you have to do some classic C incantations to get things right. It doesn't just happen. But once you get the incantations right, you get a module that you can call. Oh yeah, and you have to also set up the setup.py file for compiling the C. And Python actually is great at this. It does all the stuff for you, as long as you configure this file. So that's all built in. It's not anything super out of bounds. And finally, that's it. So that's actually the exact same code that we use between Python and C, the Python C module. And the parse select is exactly the same, no matter which language is actually backing the parsing. So we never have to care about that. And all the tricky bits are hidden inside here. So that's all great. And it's actually not such a bad experience. So definitely worth trying out if you're facing performance problems like this. It can pay off, and it has paid off here. So if you look at this graph again with a bit more of a legend here, you'll see that we went from massive variability and that some slowest 5% queries approaching a second of pure parsing to, I mean, look at the red line. It's barely visible at this point. I think it's, less than 50 milliseconds, basically. And the average is 7 milliseconds rather than more than 100. So you are literally not going to ever be able to perceive this process taking place. And previously, it was a little bit painful. So now we've covered fast. So we know we can do things fast just by writing C. So who knew? And now the problem is, what about safely? And that is a little bit of a problem. And Python is wonderfully memory safe. No null pointers laying around. And that's not the case with C or C++. We've got to watch out for these. So I've actually written a little small guide on doing this safely. And the short answer is, if you read the Python C API reference manual, you are actually going to learn something. So lesson, read the effing docs. But there are basically it boils down to two things. So you've got to know a little bit about how Python works. One bit is that you've got a reference counter. Question, raise your hand if you know how the reference counter works. All right, so like a 10% of people here, which is totally fine because you never need to care about this if you are just writing .py files. But you might want to know about it now because the reference counter is how Python is able to not run out of memory. So the moment you create an object like something like here, whenever it creates an AST compare operation right here, it's got a reference count of 1 because it's being used somewhere. And the more places you use it, the higher the reference count will be. And when it goes out of scope, that reference counter is decremented. So the moment it gets down to 0, we know we can totally throw this out the window and free up the memory. And the world is beautiful. And this all happens behind the scenes. You never need to know about it. Now you're writing C, and you're plugging into the very guts of Python. So you are going to be the reference counter now. And while you don't have to keep the count yourself because it's literally just a member on the PyObject struct, you do have to call PyDecref a bunch of times whenever you stop using Python object that you created from the Python C API. And if you don't, things won't be great, and you'll probably run out of memory in your server, and your users are going to complain that the service is down. And if you decrement too many times, you are going to end up with a seg fault probably, although that's kind of undefined behavior. So again, who knows? So you want to have an idea of how this works. But there is that payoff that we were talking about. So it might just be worth it. And that's, yeah, so just to summarize, that's the PyDecref function. You've got to do it. That's it. And the second big thing that you actually have to think about is the second thing is you've got to handle exceptions, and you can no longer do raise something, whatever. Say that's a top-level function of our C Python module that we've got, and the simple way of doing things is just call the function that you're interested in, and that's it. Which you can do in Python. Say this visit function throws, that's all right. You're going to get an exception in Python, going to get a whole exception traceback and everything. You don't get this when you write things manually close to the metal. So you have to make sure that you catch every possible C++ exception, since if you don't, again, things crash and burn. And when you do that, you also have to set that exception yourself. So basically, you have to be way more aware of how Python works under the hood. And it's not rocket science. You just have to catch the problem and set that error object. And that's pretty much it. And you see the decrefs, you've still got to remember about the reference counter. So these two things are something you are going to have to think about all the time. But just following these rules, you're going to have something that works exactly the same as in Python, way faster, 20 times faster in this case. Same ergonomics in Python. You can test it in Python the same way you have been forever. And everyone's happy. And just one appendix is that you're also going to run into the problem of having to build and compile. And so your fellow developers might be using ARM Max, but then probably production is using x86 Linux. So you are going to have to build for more than one architecture. It's kind of painful. And there is a beautiful tool that just handles it. So there is no thinking about it, really. You should use CI build wheel. Because what CI build wheel does is allows you to just define the architectures you're interested in. It's kind of a script to install any dependencies, like the ANTLR runtime in this case, because that's something we need. And this happens every single time for eternity in CI for you now. So here we use GitHub Actions. So you can see we've got a workflow that splits out into macOS, which builds both architectures, x86 Ubuntu and ARM Ubuntu. And we've just got this whole setup uploaded to PyPI, and we can install it anywhere, no problem. So that's it. So quick recap. We've tackled 4 problems: how to approach processing untrusted input. We parse it. How does ANTLR help? So it's a parser generator, and it's great. How do we use maximum performance out of our Python parser? We don't use Python anymore. And how do we interface with C++ safely? And there's these 2 rules that matter, and you should really read the docs. And that's it. Thank you.
Any questions? Few of them.
Mogą być po polsku też pytania. Może lepiej po polsku.
Nice, great talk. I think it's quite interesting interfacing C and Python. But I was thinking, are there any alternatives that you consider other than ANTLR to parse that grammar? Some other projects that might be faster? Is it like something that you consider?
Yes, excellent question. So, yes, and we have a group of people in the company who would prefer us to use Rust everywhere. That's a thing. So I actually spent a few days just exploring possible Rust solutions so that we avoid the whole pain with null pointers. We wouldn't actually avoid the pain with like the reference counter, but way fewer ways for things to go wrong. But there is one way in which ANTLR is it basically works as opposed to most other solutions, which is that there is this problem in parsing called left recursion. So if you have an expression that is references itself on the very left side, you're going to have to rewrite it some other way for most parsers to be able to process it. And this is something that ANTLR does. And it's been around for 20 years or so. So they came up with a solution for that. Every single other parser I've tried basically was not able to handle that without massive changes, manual changes to our syntax. In addition to obviously every solution has its own way of writing the grammar. So that's a bunch of effort in itself. So this was pretty much the simplest way to do things.
Cheers. So my question comes from curiosity. You solved the problem. It seems that the problem was that something was slow. And now I will guess, and you tell me which guess is correct. It was slow, so your users were unhappy because you care about user experience, or maybe you had so many users querying your system that you had to optimize, and or something else. And I just wonder, what was the initial motivation for doing this?
Yeah, so the problem with this problem is that it does not, there is no scale component to it even, because a single user will have this same problem just the same as 1,000 users. So we were actually at a very early stage with the SQL querying feature, and everyone was already complaining. So that was the blocker to actually being able to roll this feature out. And then maybe the side note about having an SQL flavor of your own is that we can then get to these problems like this query is being slow by rewriting it in a more optimized way than someone would write it themselves. But yeah, the problem is a second for parsing this single SQL query when you've got a single user was painful.
Okay, so I understand that the parser code generated by ANTLR generates a syntax tree, so some kind of structure, and then if the code is in C, the whole thing in interfacing in Python is just to pass this structure from C code, which will be a Python module, to the Python domain. So if it's just passing a structure, my question is, how many moving parts are there? I mean, in the other way, how hard would that be to generalize your work to make it work for any parser?
Yeah, so the very nice thing about this architecture is that it abstracts things away very nicely. So yeah, this ANTLR part, it handles it. This is called the parse tree. So so this is very much language agnostic. And so we could pretty much translate the same thing to anything else that we'd want. And yeah, that's pretty much the answer. This works across so many languages. And then you've got to find the optimal one. I tried this with Go, actually. The problem with Go was, Go, like you'd think is a pretty fast language. It was around 5 times slower than Python. So they were doing something wrong in there, in the parser layer, I think, in ANTLR. But yeah, this structure translates to anything.
Okay, the last question.
Okay, so you point in the parse part of the interacting Python with C++ code, there's problem with reference counter. Is there any specific reason why you decide to write this code by hand, not using Cython? Because Cython is the way to solve this if you have typed on the small layer that need to be done and do it automatically.
That's a great question. I've not considered Cython for this. I think I did, and actually I should test this out more. Basically, I think that would be a little bit harder to interface with the C that ANTLR C++ that ANTLR outputs, but I might be totally wrong. So, great pointer.
Okay, thank you, Michael, for your great presentation.